Good morning to all. Today we are going to discuss about the diversity combining techniques in wireless communication. So combining diversity means it is to improve the signal total quality of the signal. We have to be use the different antenna heights generally. But diversity reception method overcome this, and this method is divided into two categories. One is selection diversity and another one is combining diversity. So the selection diversity is best signal copy is selected and processed, and in the combining diversity all copies of the signal are combined and then decoded. So in the selection diversity, for selecting the best copy means mainly based on SNR or bit error rate, and combining model diversity, we are going to take the copies and we are going to average it or you are going to combine it. If the signal levels at an antenna elements are identical, the combiner output SNR is larger than the SNR at a single antenna element. So that also has to be focused while discussing the combining diversity techniques. First one is the selection diversity. The selection diversity is more suitable for mobile radio application because of its simple implementation. In this scheme, we can use two types of parameters. One is received signal strength indication driven diversity, and the second one is bit error rate driven diversity. In this scheme, the receiver monitors the SNR value of each diversity branch and chooses the one with the maximum SNR value for a signal detection. So the received signal strength indication diversity, we are going to measure the RSSI in each of the receiving side. In this method, the receiver selects the signal with the largest instantaneous power, or we can say received signal strength indication, and process it further. This method requires n number of receiving antenna elements, n number of RSSI sensors, and n minus 1 multiplexer. So that we can select a better antenna based on the high instantaneous SNR. The second one should be the bit error rate driven diversity. So we first transmit a training sequence as per the adaptive equalization first method. That is a bit sequence that is known as the receiver, and the receiver then demodels the signal from each received element and then compare with the transmit signal. So in the receiving side, you are going to correlate the transmit sequence, which is shown as transmit sequence here, and it should be compared with the received filter signal. So when it is comparing, based on the smallest bit error rate, the suitable channel is selected for the reception of data signal. So the next one, which is the combination of using this, is the switch diversity. The criteria RSSI or bit error rate must be calculated for all the diversity branches. This increases the hardware and reduces the spectral efficiency. To overcome this, the switch diversity is used. Switch diversity means the selection criteria of active diversity branch is monitored. So either which the RSSI driven, which one is dominating, that will be selected. So if it that will for that it will be using a threshold level. If it falls below a threshold, the receiver switches to a different antenna. So based on this, how we are going to avoid the other drawbacks which is faced while going for the previous two is by using a hysteresis or voltage. So hysteresis, it should be calculating from the difference between the lower level and the higher level. For example, it should be the threshold level is minus 20 means based on the hysteresis, with a difference of 3, it can either have up to minus 23 or it can have the minimum value of minus 17. So this is how it is going to fix the threshold, and using a hysteresis the whole time between that to avoid the unwanted going for the threshold level. Next is this combining diversity also because the selection diversity wastes energy by discarding the other copies, because we have to monitor many things, but we are going to take only one copy. So n minus 1 copies of the received signal should be discarded. This is avoided by combining diversity, which uses all available copies. So for each signal copy is multiplied by a complex weight and then added up together. So the noise power also sometimes added. So for that, for an amplitude weighting should be used. There are two methods based on that. One should be the maximum ratio combining, and another one should be the equal gain combining. So in maximum ratio combining, you are going to co-phase and sum all the received SNR with multiplied with the gain. So or we can say sum weight. So when it is co-phase, what happens is, and you are going to sum correction means the maximal ratio combining produces an output SNR equal to the sum of the individual SNR. So which will be giving advantage in calculating your received signal power. So because of this, what's the advantage is acceptable SNR can be obtained with best statistical detection of fading. Or we can say whether it will be combining the diversity. But drawback is there because high cost, each and everything is going to be weighted, means it should be recurring more fast, as well as all should be in phase. For that, it will be recurring more concern. And the second one should be the equal gain combining. It is similar to maximal ratio combining, except that the weighting circuits are omitted. Here, all branches are said to be having unity gain. So the signals from each branch are co-phase to provide equal gain combining diversity. So it is also superior to selection diversity, but it also has some drawbacks. What are the drawbacks it is having is, it is slightly inferior to MRC, since interference and noise control signals may be combined with high quality signals, as well as this particular is worse than this maximal ratio combining by a factor of 5/4 in terms of SNR. Thank you.